In this part of the Neurocomputers and Deep Learning course related to deep learning, you will learn details of convolution and pooling layers in convolutional neural networks. Let's consider the definition of convolution first in one dimension, and then we will consider convolution in the two-dimensional space. Convolution as shown with star xt convolution with Wt is defined in the continuous space as St is integral x a w t minus a dA. Notice that while the first function remains the same, the second function is reversed with respect to its parameter. This is for the continuous case. If we consider discrete case, St is defined as, here we have summation, a is from minus infinity to infinity, these are integers. We have x a w t minus a. Here there is an example showing the result of convolution and also cross-correlation and autocorrelation. F is a square function. It is the same for all these three cases. G is a function having a triangular shape, and we have the same G in all these three cases. F convolution G is defined as given here. Notice that here F is corresponding to X and G is corresponding to W. Because we have W t minus a, we are reversing the shape of the function g. Here notice that when t is equal to this point, then the value of the convolution will be 0 because the value of f is 0 here, and after this point on the value of g is 0. Because of that, the value of the convolution is 0. However, if function g is shifted, then we will have here a region for which both of the functions are not 0. So we will have some value here which is larger than 0. And as t progresses, here when t is equal to this point, it will have the maximum value as given here. And after that, as t increases, the value of this integral will decrease, and after some point, it will become 0. The difference between convolution and correlation is that while in the convolution we are reversing the function g, in the correlation it remains the same. So here instead of t minus a, we will have a minus t. So in the cross correlation, this function g is not reversed. Again, we are finding what is the integral of the multiplication of these two functions. First it increases and then decreases, and when t is equal to this point, it will become 0. If we are applying autocorrelation, then we are using g as the first function and also as the second function. In autocorrelation, instead of having different functions as f and g, we have a single function. It is autocorrelated by itself, and the result of the autocorrelation is given here. Convolutional neural networks are going to be applied mostly on images. We are considering here convolution in two dimensions, but depending on the dimension of the tensor to be used, convolution in higher spaces may be considered. The convolution of the functions I and k in discrete space is defined as summation m is starting from minus infinity to infinity integer, and is also changing from minus infinity to infinity. We are considering the value of the function I at point mn, and also the value of k at point I minus m and j minus n. They are multiplied and summed up. Due to the commutativity of convolution, it can be written equivalently as we can write instead of I m n, here we have I minus m and j minus n, and instead of k we have m n. However, if we are using correlation instead of convolution, in that case, in the formula, we have I plus m instead of I minus m, and j plus n instead of j minus n. This is the definition of the cross correlation in discrete two-dimensional space. Notice that cross correlation is corresponding to convolution without kernel flipping. In fact, in the convolutional neural networks, correlation is used. That means that we are using filters, but we are applying them without kernel flipping. An example of 2D convolution without kernel flipping is given here. Suppose that we have two-dimensional input. For example, this may correspond to pixel values in an image. We have values A, B, C, D, E, F, etc. And here is the filter. It is also called as kernel. This is a 2x2 kernel, and we have values W, X, Y, and Z. If we apply convolution without kernel flipping, it means that correlation with the filter. When we apply this kernel at the input at this point, we have the inner product of the data in this part of the input and the kernel. That means that the result of applying this kernel at this point is AW plus BX plus EY plus FZ as written here. If we shift the position of the kernel to this position, in that case, by applying the kernel, we will obtain BW plus CX plus FY plus GZ as written here. If we shift one more, then we will have the kernel applied here. In that case, we will have CW plus DX plus GY and plus HZ. Similarly, if we shift down and if we apply the kernel, we will obtain these inner products as written here. In this case, we restricted the output to only positions where the kernel lies entirely within the image, called valid convolution in some context. Here, notice that the size of the output is decreased by 1 if we consider the columns, and also by 1 for the rows because the kernel is 2x2. If we do not want to reduce the size of the output, in that case, we are adding extra rows having value 0 and columns having value 0. This is called zero padding. And when the kernel is applied, we will have an output having the same size as the input. This is called zero padding. As an example, consider CMYK image, which has 4 layers. So depth is 4 here. We are going to find the convolution layer feature maps by applying filters. This results in detecting the same feature at different positions in the input image. Here we have 4 layers in the filter having 2x2 size, and if we consider the point where we are going to apply the filter, consider all these values as a vector and all these values in the filter also as a vector, then we are finding the inner product of the vector having these components with the part having the same size in the corresponding part of the image. Convolution is applied in 3D. Convolution filters should cover also depth. Here we have 4 layers in depth, so the convolution filter has depth. 2x2 multiplied by 4. This is the depth. This is the size for a single filter. If we are using more than one filters, then a separate feature map is obtained for each filter. In the next layer, that is the layer n+1, that is adjusted considering the number of feature maps in the previous layer. For example, on this image, by applying a filter like this, we may obtain such a feature map in the next layer. However, with some another filter, we may obtain a different feature map. Then the collection of these feature maps will be corresponding to the output of the convolution layer in the network. After convolution is applied, we are using an output function, which is a nonlinearity. Previously, in the multilayer perceptron, we used sigmoid function and also tangent hyperbolic function, as shown here. This is the sigmoid and this is the tangent hyperbolic function. Remember that sigmoid function is defined as 1/1 plus exponential minus x, and tangent hyperbolic function is defined as 2 times sigmoid minus 1. If we consider the shapes of the sigmoid and tangent hyperbolic, they are S-shaped, while sigmoid is having value between 0 and 1. Tangent hyperbolic has values between -1 and +1. In convolutional neural networks, rectified linear unit, ReLU, is used mostly instead of sigmoid or tangent hyperbolic function. ReLU function fx is defined as maximum of the 0 and x. ReLU simplifies backpropagation algorithm, makes learning faster. Because of that, this is the preferred option, and this is the shape of the ReLU function. For x up to 0, we have the value of the ReLU function 0, and after 0, the value of the function becomes same as the value of x. Instead of ReLU, sometimes soft plus is used, which is defined as ln 1 plus e to the power x. This approximates ReLU and it is differentiable. If we apply filter and then nonlinearity, this is called detector stage. And after that, we have a pooling stage, which may be max pooling or average pooling. In the max pooling, we are considering the maximum value. This is the output of the detector stage. And in max pooling, we are considering the maximum value on which the pooling filter is applied. Here, the pooling filter is considering these three connections. So we are considering those values 0.1, 1, and 0.2. The maximum is 1. If we shift the filter 1, then we will have 1, 0.2, 0.1. Again, the maximum is 1. And if we shift one more, here the maximum is 0.2, etc. Instead of finding the maximum value here, the average of these values can be calculated. This is called average pooling, but mostly max pooling is used in the convolutional neural network. Instead of shifting by 1, if we shift with stride equal to k is larger than 1, the size of the output obtained by the pooling layer will be decreased. This reduces representation size by a factor k. Suppose that pool width is 3 again and stride is 2. In that case, we are shifting the filter by 2 while we are applying it. So here we are considering this 3 because pool width is 3. We are considering this 3 and the maximum is 1. Then shift it by 2. We are going to apply here 0.2, 0.1 and 0. The maximum is 0.2 and again shift by 2. The maximum is 0.1. The normalization step in convolutional neural network is optional. It is used in earlier CNS. However, in recent CNS, normalization is omitted. For example, contrast normalization between or across the feature maps may be applied. This equalizes the feature maps. For example, here the feature maps before contrast normalization is given, and after contrast normalization, we may obtain such a feature map. Consider the layers in the convolutional neural network. The receptive field of the units in the deeper layers of the convolutional network is larger than the receptive field of the units in the shallow layer. For example, if you consider convolution with filters of size 3, then this unit in the convolution layer will see a receptive field having only 3 elements. Also same for the other neurons in the same level. However, if we go one level further, notice that the receptive field of the neuron enlarges. So here, in the receptive field of this neuron, we have 5 neurons in the input layer. However, if the input is 2-dimensional, the receptive field for this one will be 3 by 3, and for this one will be 5 by 5.